And by the way, this is called in many different names, like LCR, LRC, CRLR, LC. Yes. So I don't know which is like the standards. But what it means is it's a circuit that's made of these three components. So you have a resistor, R, and a capacitor, and then L, which is an inductor, connected to some voltage source. Usually you put curly E, script E. And it's a function of time, so we'll just say script E. That's called the RCL circuit. All right, when you try to solve a circuit and you want to find out the current flowing through it, what kind of rules do you use? Ohm's law is one thing. Another one?
KCL, KVL.
KCL, KVL, very good. Yeah. So we use the KVL and KCL, Kirchhoff voltage law and Kirchhoff current law. What does the Kirchhoff voltage law say?
That around the loop, the sum of the voltages will be 0.
Yes. So if you go around the loop, sometimes the loop will be providing the voltage. Sometimes there will be a voltage drop. And but if you add them up, you get 0 as the total. So we can get a differential equation by doing that. And let's see how that's done. So someone mentioned the Ohm's law. Let's start with the Ohm's law. What is the voltage drop across a resistor? V equals to? IR. And we're going to put minus because there will be a voltage drop. And then what about an inductor? Do you know what an inductor does?
I know it's like a coil.
It's a coil around either a magnet or some metal, right? And what it does is, like, because the metals can be magnetized, if you change the current, then it will try to change the magnetization of the metal, which it doesn't like, right? The materials cannot simply just immediately change their magnetic direction, so it tries to preserve the way it's magnetized, and due to that, an inductor will try to go against any change in the current, right? So you can kind of see that the voltage drop across an inductor will be due to any kind of change that you want to have for a current. So how do you write the change of a current? Yeah. dIdt, yes. Put that. And there should be, since these are proportional, there should be some proportionality constant, and we call that the inductance, measured in Henrys, and it should be minus. Again, because it's a voltage drop. Okay. Now, what about the capacitor? So there, usually the way we write down voltage drop around capacitors is like we don't write that. We talk about the charge across a capacitor, right? How does charge happen on a capacitor? Yeah.
Voltage times the current.
Yeah. So you apply higher voltage, then more electrons gather on that plate. It's like it's modeled as a metal plate, right? And then you have more charge, then you have more electrons on one side of it. So the rule for that is really charge is equal to capacitance times the voltage. And if you solve this for the voltage, you end up with the voltage across the capacitor equals to, you have to divide it, so it's like 1 over C times Q. But again, this is a voltage drop, so we're going to put a minus in front. So just think of this as a minus there. So that's the voltage drop across the capacitor. And now we're going to use the Kirchhoff voltage law, which is to go around, add them up. So you're going to get, first, this is the voltage source, so it provides voltage, and then all these voltage added up should equal to 0, but these are voltage drop. They all have negatives. IR minus L times di dt, then minus 1 over C Q equals to 0. And then we can move all the negatives to the other side to make it all positive. So this is what we get. We get, I'm going to write this first. Okay, so I have L di dt plus R times I. I'm going to write down IR as R times I. And plus 1 over C Q. Now, what's usually given to us when we're trying to solve this? To solve this, I mean, we want to find the current flowing at all times. And although the voltage changes with respect to time, this is usually given to us, right? The external voltage is given to us. The inductance, resistance, and capacitance are all usually given to us. And we want to find out what the current is. However, there is still some problem here because the charge across the capacitor, remember this is an AC current, I wrote an AC current, so if the voltage direction changes back and forth, then this one will also change with respect to time, right? So Q is a function of time that would change, and you have I, which is a function of time, that's the current with respect to time, and you have two functions that we don't know. We don't know what Q is. We don't know what I is. So at first, this looks like something that we haven't dealt with before. It looks like a system. However, if you think a little bit more, you can kind of think about the relationship between the I and Q. So charge across a capacitor and the current flowing towards to it. What kind of relation do you think there is?
Direct.
Huh?
Directly proportional.
Directly proportional. Okay, getting there. Any other ideas?
Inversely.
Not inversely. So what's happening is this. You have a capacitor and you have all these electrons gathering on one side. Right? There's like holes here. But how is this electron gathering here? It's carried by the current, because current is the flow of the electrons, right? So you can see that for a capacitor, the reason that there's the charge across it is because charge is really sum of all the current flowing to it. That's how you can think about it. Right? And you can just differentiate both sides and get the following relation that I, the current, is equal to dq dt. Right? You just differentiate both sides and you immediately get that the current must be the rate of change of the charge. And then, now let's look at this again. This itself is not a good equation because, if you replace Q by integration, then this is an integral differential equation which we never have solved before. So we need to turn this into a differential equation that we've done before, and one way to do it would be actually differentiate both sides so that this will be differentiated, this will be differentiated, this will be differentiated, and this will be differentiated. And if you think about what the resulting equation would be, it would be like L, now it's differentiated twice, and then R is differentiated once, and then 1 over C, and Q is differentiated, which is I equals to the external voltage prime. And this will be the master equation that we will be working with. But look at this equation. It looks very similar to what we've been doing before, which is the mass spring dashpot system. I'll just call it mechanical vibration. So for the mechanical vibration, here's what we had. The master equation for that was mx double prime plus cx prime plus kx equals to the external force. And comparing the two, we can immediately deduce the following, that let me erase this left side. So we can immediately deduce the following. That here's the mechanical vibration, and here is the RCL circuit. And what was taking the role of mass, the L is doing it. Inductance is doing the same thing. So mass corresponds to the inductance. C corresponds to resistance. And then K corresponds to what? Huh? 1 over C, right? But this C is supposed to be capital C. This is small, lowercase c. This is capital C. All right. And then finally, the external force, it corresponds to the derivative of the external voltage, or the input voltage. So there's the input voltage, and if you differentiate, it corresponds to this. And this is just by purely by just comparing the thing. And what it means is like the following. If you have some system with RLC, different values of RLC with some input voltage, and you observe its motion. Its motion, it's current. It's current from here. Then its current will have an immediate corresponding solution in the mechanical vibration with the corresponding M, C, and K values with Fe. Which means we learned in the mechanical vibration that there are 3 types of motion if it's unforced, right? There's the underdamped, overdamped, and critically damped. Same thing can be applied here. Okay. Now, we also learned that for this one, there is the transient solution and the steady periodic solution, right? There's also a transient current and a steady periodic current. So, in other words, this one will have a solution structure that looks like I transient, which decays to 0 very fast, plus I steady periodic, which perseveres, and that's because of the input voltage continually feeding energy, so it gives you that. And as I said, often what we're interested in is this one, because this quickly dies out, and what we want to know about this is what's the amplitude, what's like the phase angle. Those are the things that you end up thinking about. Right. So it's like 2 systems are basically the same thing, so knowing one really well allows you to know the other as a bonus. Now, there is a formula I wrote down without deriving, and actually today I spent some time writing down the calculations because I want you to actually see how it's done. But it's like exactly same as some exercise problems you solved before except that I'm using letters instead of numbers. So one of the formulas that we found out from the mechanical vibration was that the X steady periodic solution looks like F0 divided by square root of K minus M omega squared plus C omega squared times cosine omega t minus alpha. And I didn't even write down the formula for alpha. However, in the PDF file I just sent out as an email today, it has the formula for alpha. Not that I want you to memorize it or anything. Just follow the calculation, see if you can do it on your own if you have to. Because it will deepen your understanding of how everything works in this system. All right, so this will have a direct correspondence in the steady periodic thing. But to do that, we will have to modify some things a little bit. So, so let me write over here. So usually our input voltage will be modeled as, again, some V0, where the V0 is the peak voltage, and cosine omega t. That's how we're going to model our input voltage. Yes?
Oh, no.
Okay. And then because we have to differentiate it, if we differentiate it, omega comes out and cosine differentiates to negative sign, so you end up with negative V0 omega sine omega t. And you know, this is a sinusoidal curve, that's a sinusoidal curve. So if you took this curve and if you took a cosine V0 omega cosine WT omega t and shifted in some direction by 90 degrees, you're going to get this. So it ends up being like the right side is V0 omega cosine omega t minus, actually plus 90 degrees. I think I'm right, because the cosine graph, if you go 90 degrees this way, you end up with a negative sine graph, right? So this will shift everything to the negative 90 degrees direction. Okay, so that's what you're going to do. And notice that for this one, we had to solve for the right side being F0 cosine omega t. That was without this, right? F0 cosine omega t was the external force when we solved it. So unfortunately, when you use this formula for alpha and use it for this case, they will be off by 90 degrees. Well, so let's not worry about the alpha. But what's happening is this. We're going to end up with, because instead of F0, we have V0 omega working like the F0. The top one will be V0 omega. And then we can use this dictionary here. Okay, so for K, what should we replace K by? 1 over C. Minus, what's the M? L and omega squared. How about C? R omega squared. And it will be cosine omega t minus, I'll just use alpha, but these two are different. They actually differ by 90 degrees. And then furthermore, what we can do is we can divide top and bottom by omega. So if you divide omega top and bottom, this will go away. And if you divide, so let's see. If I divide by omega, and you bring this inside the square root, it becomes squared, right? And when you bring it inside here, what's going to happen is that omega will be It's just like same as dividing this much by omega. And this omega square will be completely gone. And the result will be like V0 over square root of 1 over C omega minus L omega squared plus R squared times cosine omega t minus alpha. And by the way, you can get the same exact answer by, instead of using this formula, you can just solve it for this one. You can just leave it like this, the right side like this, and you leave LR 1 over C as it is, and you just do the method of undetermined coefficient. It's a huge calculation, but at the end of the day, you will get exactly this. And as a bonus, you also get a formula for alpha, which will turn out to be the following. Alpha would be tangent inverse of this thing here, but it's this one first. L omega minus 1 over C omega divided by R. That's what's going to happen for alpha. All right. Now, any questions so far? Okay, if you're okay with it. Now, let me point out some more things that you may have seen before. Okay, so 1 over C omega. Has anyone seen this? 1 over C omega? No? Well, here's something that you know, which is that we know the formula that period is 2 pi over omega, so that frequency is 1 over t, which means you flip this, so it's omega over 2 pi, which means that omega is equal to 2 pi f. Now, if you use that and rewrite 1 over C omega as 1 over C times 2 pi f, or in a way that you're more familiar with, you put the C at the end, you write 2 pi f C. What is this? Yes?
Isn't that for inductance?
Huh?
Like for the inductor? Isn't that the formula to get the inductance of a circuit?
Yes, it's what is that called though?
A differential equation?
No. This thing right here.
Impedance?
Yes? Not
Isn't it
impedance.
like the inductance called by the capacitor? Something along that line?
All right, something. Does anyone know the exact terminology? You guys are close. Okay, so this one is called capacitor reactance. Okay, and it's named as XC. Okay? And the same thing can be done for the other one, which is L omega, which is omega is 2 pi f, so again you can rewrite them as 2 pi f L, and that's called inductor reactance. And then using these you can rewrite the thing that we have here as the steady periodic solution. The current steady periodic solution will be V0 over square root of, and usually people write R squared first, so I'm going to write R squared first, plus XC minus XL. And by the way, because this is squared, it doesn't matter if you do XL minus XC or XC minus XL. They're just off by a negative sign, so it's either way. And cosine omega t minus alpha. So that's what you get as the steady periodic solution. Now, what is this thing called down here?
Impedance.
That's called impedance, yes. So you see that the impedance here usually goes like that. Now, once you've understood all this, assuming that you actually did the calculation, and it's trust me, it's worthwhile to do this because LCR circuits are very important for all engineers to know. So please try to derive this. But then another thing that I propose is try to go back to your physics textbook and see how it explains this formula. It's a little bit more cryptic than what we did. Here we just do the calculation, and of course that's the answer. That's all it says. But your physics textbook, because it cannot talk about differential equations, it tries to explain it as like, oh, the volt or the current inside the inductor lags behind by 90 degrees, and capacitor is leading by 90 degrees. All these things are there, and it tries to kind of use this phase diagram to show you why you end up with something like a Pythagorean theorem. And that will actually make more sense now that you can kind of have confidence that this is indeed what is happening. And by the way, this formula here would be alpha equals to tangent inverse of the XL minus XC over R. Now, there's one more thing that you get as a bonus if you actually do the calculation. You'll see that when you solve this, how do you solve it? You solve it by saying that the particular solution is something times cosine omega t plus something times sine omega t, right? And you plug it into the left side, set it equal to this one, and say, oh, therefore, you set it equal to this one, and therefore the cosine term would have 0, but the sine term at the end of the day should equal to this, and you do all these things. If you do that calculation, then you'll see that A is always positive. B could be negative or positive, which means that the resulting solution in that quadrant that I talked about, 0, pi, negative pi, and 0, it's always here. So you never have to modify it. So that's really convenient for us, because you don't have to plus pi or negative pi when it comes to this. On the other hand, this differs by 90 degrees. So if you actually do this, you'll see that this phase angle is always from 0 to 180 degrees. Okay? It's from here to there. You can also see that. Okay? So try to see that. And therefore, what it's saying is that when you have an input voltage, the current inside the RCL circuit is always between, has the phase angle between negative 90 degrees to positive 90 degrees. Okay, that's another thing that you see here. Now, let me ask some more knowledge here. So I said, I want to see how much you remember from your physics class. So you learned something called RMS voltage, right? What's the relationship between the peak voltage and the RMS voltage? Yes. Yeah. Where this V0 is either people write VPK for the peak voltage or the Vmax, max voltage. Okay. So this formula right here is saying the following. This formula is also saying to us that the max peak current is V0 divided by Z. Right? Because this coefficient is the peak. This coefficient right here is your I0t. Right? So that's your peak current. And you just, since the denominator is Z, it's just that. And also, in terms of the root mean squared voltage and current, it's like this. Just because you just divide both sides by square root of 2, then that gives you root mean squared. And then then if you compare this with the Ohm's law, which is I equals to V over R, you can kind of see why people like the impedance, right? Because Z is like working like the R. Although there's a difference, this depends on the input voltage. So Z is different for each the input voltage is frequency. So see, the formula is XC and XL, they both have the input voltage is frequency. So they're different. Whereas if you just have a resistor, it doesn't care. The current flows uniformly just by dividing by R. Is there anything else I want to say? Okay, I think that's